The explosive core of a nuclear weapon relies on very specific materials, typically highly enriched uranium or weapons-grade plutonium. When a single atom of one of these heavy isotopes splits apart, it releases a massive amount of energy, along with 2 or 3 free, high-speed subatomic particles called neutrons. Left on their own, those free neutrons will fly outward and strike surrounding nuclei. Those atoms then split, releasing even more energy and even more neutrons, creating an exponentially multiplying cascade. Physicists measure the viability of this reaction using a concept called critical mass, governed by the effective neutron multiplication factor. This is represented mathematically by the letter K, which simply calculates the average number of neutrons from each split that successfully go on to cause another split. The math here defines the threshold of a weapon. If K is less than 1, the reaction dies out. If K is exactly 1, the reaction is stable and self-sustaining, like in a nuclear power plant. But if K is greater than 1, the mass achieves supercriticality, and the reaction cascades out of control. The primary engineering hurdle isn't getting the reaction to start, it's stopping it from starting too early. These heavy isotopes undergo a steady rate of spontaneous fission on their own. If you try to push 2 pieces of subcritical material together too slowly, the natural radiation will heat the metal, melt it, and blow the assembly apart before it ever reaches optimal supercriticality. In weapons design, this premature failure is known as a fizzle. Building a working weapon requires forcing the fissile material into a perfectly dense, supercritical state in a fraction of a microsecond, so that the chain reaction can fully execute before the heat destroys the machine itself. The first mechanical solution to achieve that microsecond timing was the gun-type fission weapon. The interior of this design looks exactly like a piece of artillery. Engineers pack a hollow projectile of highly enriched uranium into a heavy steel barrel and detonate conventional explosives. The projectile shoots down the barrel and slams onto a static uranium spike at the far end. The 2 pieces interlock to form one instantly supercritical mass. While mechanically simple, this method is severely inefficient. The uranium is entirely uncompressed. Because the material's density hasn't been increased, the gaps between the atomic nuclei remain wide, meaning the newly freed neutrons can easily escape the mass without colliding. To ensure enough collisions happen before the bomb blows itself apart, engineers have to pack the weapon with a massive, heavy surplus of enriched uranium. To reduce the weapon's sheer weight and extract more explosive yield from the fissile fuel, physicists had to abandon the artillery approach and instead find a radically new way to compress the metal itself. That shift in strategy was accelerated by the introduction of plutonium. Plutonium is a highly active fuel, but its spontaneous fission rate is so fast that if you try to shoot it down a gun barrel, it will melt and fizzle while still in transit. It requires a much faster assembly method. The solution is implosion. In this design, the plutonium sits in the center as a subcritical hollow sphere called the pit. Surrounding this pit is an intricate outer shell made of geometrically shaped conventional charges. When those outer blocks detonate simultaneously, they push a perfectly uniform symmetrical shockwave inward. This crushes the plutonium pit, drastically increasing its physical density and forcing the atomic nuclei tightly together. At the exact microsecond of maximum compression, a small vacuum tube called a neutron generator injects a perfectly timed burst of free neutrons into the crushed pit, kicking off a vastly more efficient chain reaction. Implosion solved the spontaneous fission problem and yielded a far more powerful explosion. But early weapons designers quickly recognized that this massive release of energy could serve a secondary purpose. By adding a separate nuclear fusion reaction to the system, engineers learned they could multiply the explosive yield by hundreds or thousands of times. In a staged thermonuclear weapon, the entire implosion device we just explored is demoted to a single component. It becomes the primary stage. It acts as a remarkably complex spark plug. When the primary detonates, it floods the opaque channel surrounding it with an intense burst of X-ray energy. These X-rays instantly vaporize the plastic foam lining the interior, turning it into a superheated plasma. This creates a massive ablative force, like an inside-out rocket engine, that violently crushes a second cylindrical capsule at the bottom of the casing, packed with fusion fuel called lithium deuteride. As this secondary capsule is crushed, a dense fissile spark plug seated in its absolute center is forced into supercriticality. It fissions, providing the extreme heat and the exact neutron flood necessary to ignite the lithium deuteride fusion reaction. The thermonuclear weapon represents an absolute extreme of engineering. The violent splitting of heavy atoms is harnessed solely to generate the exact temperature and pressure required to fuse light atoms together. All of this subatomic choreography occurs inside a steel casing in fractions of a microsecond. The outputs of those reactions then instantly interact with the outside world. This graph illustrates the sharp variation of pressure in excess of ambient pressure, measuring the explosion's kinetic energy. This energy violently displaces the surrounding air, creating a hydrodynamic shockwave that delivers a devastating peak overpressure to the surrounding environment. Alongside the pressure wave comes the thermal radiation. This invisible light and heat accounts for a massive proportion of the total energy released, rapidly ionizing the air into a fireball that appears many times more brilliant than the sun. Finally, the reaction emits prompt initial radiation in the form of highly penetrating X-rays and gamma rays, followed by the longer-term decay of radioactive weapon debris, known as fallout. In the immediate blast zone, the combination of immense mechanical pressure and searing thermal energy instantly overcomes the physical limits of conventional structural integrity. Buildings are flattened into kindling, and concrete is pulverized. By mastering the precise manipulation of critical mass, symmetric geometry, and subatomic timing, humanity engineered a way to temporarily ignite the destructive power of a star, right here on Earth.